Today's speaker in the Rutgers Experimental Math Seminar is one of the foremost experts in the world on Ramsey Theory, Aaron Robertson, who wrote a great book, Ramsey Theory and the Integers, and now is about to write another book on Ramsey Theory. We'll talk about Ramsey Theory and data mining. Thank you.
Okay, so thank you, Alex. I am going to be going to, I'm on an iPad, and so when I share the following content, I am going to disappear from video. So you'll be listening to a disembodied voice give the lecture, but that's so I can annotate better. So let me share. Okay, so I am speaking about data mining and Ramsey theory. And this is talk is based on a forthcoming book that I spent the last couple of years writing, Fundamentals of Ramsey Theory. And this talk is based on contents of the book, some of the contents, and it's not my own research. So I'll point to where the data mining part comes in and who did it. So I want to start with the Bible Code. So this is was a bestseller about 25 years ago. There were two sequels to it, Bible Code 2 and Bible Code 3. This was by Michael Drosnin. If you can pick out the details of this picture, so those are, I suspect, I do not read Hebrew, but that is part of the Bible in Hebrew, I suspect. He searched through it in Hebrew, but I'm going to pretend that it was in English when I explain what's going on. And you can see that he's got some boxes around certain letters. And what he is claiming in this book is that there are secret messages in the Bible. So they were encoded into the Bible and predicted events that occurred. And his method of looking for these secret messages, he called equidistant letter sequences, so, or ELS for short. So the question is, well, first let's look at kind of get a flavor of what he's saying. So this is an excerpt from the book. And so he's claiming that the words twin towers and airplane and it caused to fall, knock down are all encoded in the Bible in these equidistant letter sequences, so the ELS. And then, you know, he finds other words, Bush, Arafat, Sharon, all in the Bible. And so he claims that the Bible is already had these in there. And so it is true that these are in fact in the Bible. That's not the disputed part. And so the question is, what's going on? Okay, so an equidistant letter sequence is an arithmetic progression. So what he's looking for are letters in some equally distant sequence. So A and D are positive integers, and we have in some position, so here's starting position, that if you skip every D characters, you get these secret messages. So for example, if you wanted to look up happy in the Bible, I'm sure you would find it somewhere. We want the number of characters between them to all be the same. Now, since I work in Ramsey theory, typically we think of things in terms of either set partitions or equivalently in colors. And so these letters you can think of as colors. And so if you're looking in the English language, there are 26 colors. And so essentially what you can view this as for a starting point is take all of the characters in the Bible. So get rid of any commas, spaces, any kind of punctuation, and each space is some color. And we're looking for some kind of color sequence in arithmetic progression. Okay, so here is, no need to read this, but this is an excerpt, not from the Bible, but from the Bible code. So this is a page from the Bible code, and I didn't count, but I put it into Word, and there are 7,337 letters. So get rid of the punctuation and everything. Okay, so I'm going to look at that. I've got that many characters. Well, it's not difficult to show that the number of k-term arithmetic progressions is something like this, and you can be more accurate. I don't want that symbol. You can be more accurate, and by doing that, you'll get that in that among those 7,000 plus characters, there are about 9 million four-term arithmetic progressions. So just different choices of A and B. And there are about 6.7 million five-term arithmetic progressions. Okay, so let's assume each of the 26 colors is equally likely. So this is not the best assumption, because we know that the letter Z is not as likely as the letter N, for example. But what I'm actually going to be doing is underestimating the probability that something occurs. So if I have wanted to look at the probability that 4 random spaces spell some 4-letter word, say math. Now, in the Bible code, he also allows backwards, or this. He also allows diagonals, which really depends a whole lot on how the book is printed. So I'm not quite sure what that means, but I'm just going to restrict to forwards or backwards. And so the probability that this happens is 2 over 26 to the 4th. And if I wanted to change this to a 5, I'd get to the 5th power. Okay, so if I wanted to know in that excerpt of 7,000 plus characters, how many times do I expect to see the word math? Well, each has probability 2 out of 26 to the 4th, and there are about 9 million. And this works out to be about 39 times I should observe this in that excerpt. So I would not be surprised to see the secret message math in that page. If I wanted to say, look at the 5 letters, let's say our favorite 5-letter word. If we're looking at that, then we've got 2 out of 26 to the 5th and about 6.7 million. And that is slightly over 1. So we would expect to see Doron's name in there as well. Okay, so what I did is I searched for a 4-letter word and a 5-letter word in that excerpt. And I found them crossing each other like he ascribes meaning to in his secret letters or secret messages. And so here is what I found. Now, I think I used different words. So this is in his own book. The secret message code is crossed with the secret message fraud in his own book. And so what he was doing by writing this book was telling you he was writing a fraudulent book, but no one ever found out. So these are actually in arithmetic progressions. We have fraud crossed with code. Now, this is not surprising. These are not secret messages. What's being done is we have a large body of text. We have some pattern in it, and we're subscribing a meaning. And so that's what I want to talk about here is this. Ramsey theory says that when we have things that are large enough, certain structures have to happen. And so I want to talk about that before getting into kind of this data mining, which is really what's going on here. You have a huge bunch of data and they're looking for patterns. That's what the Bible code boils down to. Okay, so a little bit of basic Ramsey theory. So in the last analysis, we looked at expectation and how many times things were expected. I didn't guarantee certain words would happen, but if I have a large set of words, I can probably guarantee that. But I want to look at what is called van der Verden's theorem. And so what this says is let K and R be positive integers. There exists I'll say minimal integer W. So this is based on K and R. Such that every R coloring of the integers, and I'll use 1 through W, but it's any W consecutive integers, admits a monochromatic K-term arithmetic progression. So in the Bible code, if I'm looking for, say, the word math, in order to apply van der Verden's theorem, I would have to consider M, A, T, and H to be all the same color. And then what I would have to do is I would have to deduce that the particular sequence MATH or HTAM exists among this monochromatic structure. So van der Verden's theorem guarantees monochromatic, but doesn't directly apply to the Bible code. However, it is the basis of how we can guarantee something now. This is no longer that we expect it to happen, it's that it must happen, provided W is sufficiently large. And so
even the improved one by Gauss are very, very far from the actually probably true one. So
that's true. So the current best is from last year. Somebody improved it to 2 to the K. It was 2 to the K over K to the epsilon, but it's been improved. And so this, I'll use 2. 2K. So that's Gowers, and that's very far from it. And Ron Graham had conjectured that he believes it's more of the order 2 to the K squared. But the gap obviously between these is huge and very difficult, I'm sure, because Gowers' result was improving this from a tower that grew with K. So this is a finite tower always.
What about the R dependence?
So if you want R, this I still think holds, and that R creeps in here. So what we're doing is we're unraveling a bunch of logs that's coming from Fourier analysis. And so that's where that dependence comes in, which is interesting.
Thank you.
Yep. So the Bible code deals with sequences, but the guarantee also holds just for random colorings of graphs. So what we're doing is I will restrict to coloring edges. For those who are interested, this works with hypergraphs and hyperedges too. But for what I'm going to do, I just need the edges. So this graphic shows a bunch of graphs. And if you look closely, you'll see that there's a bunch of different colorings there where I'm using 2 colors. So I'm coloring an edge either blue or red. So the notation I'm going to use, this is the complete graph on n vertices. So meaning that all possible edges are in the graph. And when I talk about K3, which is this, I will refer to it as a triangle. So it's the only one that's a polygon. Okay, so I'm going to 2-color the edges, and here's a bunch of ways to 2-color the edges of K6. There's a reason for that, but we don't need it. And so where does this come from? This comes from Frank Ramsey, which is where obviously Ramsey theory gets its name. And his original proof was not in terms of graphs. So graph theory was not quite popular yet. So the first graph theory book was published just a few years before he did his result. So his result is pretty tricky to read because his first theorem has to do with hypergraphs and hyperedges. And so he's talking about sets of sets. But here's the result. I'm going to restrict to just edges. And we'll be using Ramsey's theorem and a result based on it somewhat going forward. So Ramsey's theorem says, I'm going to restrict to the symmetric case. So K and R, positive integers, there exists a minimal number, I'll call it N, but it's based on K and R, such that every two coloring, or R coloring, of the edges of Kn admits a monochromatic K sub K. So there's a complete subgraph that's monochromatic, regardless of how you color. So for just a quick example, if I think of...
Aaron, I'm just curious. Did you actually try to read and understand the original paper by Ramsey?
Oh, I did, yes.
Oh, and you understood it?
Yeah, it's just slow going. Yep. So let's look at six vertices. And so oftentimes Ramsey's theorem is referred to as a generalization of the pigeonhole principle. So this is where it comes from. If I'm standing at one vertex X and I look at the other five, then I know using just two colors, there's some color that appears three times. And so I'll say it's red. Now, because of that, if any of the edges here or here or here are red, then we have a red triangle. And so we would say, okay, to avoid a red triangle, they all need to be blue, and then I have a blue triangle. And so here is the smallest case that would show that this number for 3, 2 is less than or equal to 6. And in fact, it's equal to 6. So you can find a 2 coloring on 5 vertices with no triangle. Just the pentagon, the edges are all colored one, and the interior edges are all colored the other. You can't have a triangle. Okay. That means, again, that if we have a large enough number, that some structure has to occur just because of size. So it's the same kind of framework as van der Waerden's. Have enough letters or have enough numbers, integers, and I'm trying to partition, meaning color, some structure has to occur. So you can't have everything disordered. There is going to be some kind of pattern. Now, what we need is a result due to Goodman about how many monochromatic triangles are there. So Ramsey's theorem tells us that I have a guarantee for a triangle. Goodman's result tells me, well, actually, you have a whole lot of them. So this one is every two coloring. So this is only restricted to two colors. Recently, somebody extended the argument to three colors, but that's difficult. And I think I'll do a brief sketch of the proof to show you why. So every two coloring of the edges of K sub n admits, I'll write it as this many monochromatic triangles. So we actually know what the exact formula is here. It's based on n mod 4. You just have slightly different cases. So this not only says that we have a triangle, we now have a lot of them. And so if I'm looking for patterns that can happen, I have to be aware that I'm going to have a lot of patterns happen just because of the size. So it's not a single one anymore. So the brief sketch of this result is the observation that if I have a triangle that's not monochromatic, then it's one of these. And how can I describe this? Every non-monochromatic triangle has two vertices, exactly two, which have different colors emanating from it. So the number of monochromatic is going to be the total number of triangles, n choose 3, minus the number of ways I can have a vertex. So vertex I has Ri red edges, and necessarily these are the blue edges. So if I count all of the ways where I can have a red edge and a blue edge, and I'm dividing by 2 because I know that each of them has 2. So I'm double counting the non-monochromatic triangles this way. And now it just becomes an optimization problem, and it's easy because this is, each one's the area of a rectangle. So we've got some kind of hyperbox that we want to, in this case, maximize. And so they're all going to be about n-1/2. And so this is where the mod 4 comes in, because you're going to have a divided by 2 and a divided by 2. And so it's just a little bit of finagling to make these integers. And once you simplify this, you'll get this result, meaning I have some kind of minimum number of monochromatic triangles that have to occur. Okay, so now we're going to get to some kind of motivation for we might see patterns and we might believe there's something, but that doesn't mean they are something. It doesn't have to have meaning. So in the next slide, I have a couple of pictures that I've put up. I just want you to look at the picture and think about what your brain sees. So don't analyze the picture. That's not what I'm after. What do you see? And so I suspect that most, maybe not all, but because I suspect you see an eye here and some kind of horse, right? And then on further inspection, you realize that the eye is actually a drain with soap, and you realize the horse is a cloud, right? So even though it looks like an eye and a horse, that's not what they are. It's a drain and a cloud. And we don't want to see something and believe it just because it looks like it. And so what you just went through is called pareidolia, and your brain is trying to make sense of something new. And so it's actually a useful evolutionary technique for us to, if we see something, we try to frame it in what we know. But for us, I want to be thinking about mathematical pareidolia. And so observing a pattern and ascribing a meaning to it. So like you saw the sink, you ascribed it as an eye, even though it was a sink, even when there's no meaning. So if we're putting these things together, what we're looking at is, I know from Ramsey theory that if I have big enough things, that certain structures have to occur. Ascribing a meaning to it, like for example, the Bible code did, would be what I call mathematical pareidolia. You see it, yes, it occurs, but that doesn't mean it means something. Ramsey theory tells us it just has to happen. And that's what this says. So it follows this tenet. Patterns will emerge. We need to make sure we don't apply some meaning to a pattern that occurs. So for example, I've got K sub 7 here. And if I just start randomly coloring edges, so I'm not really thinking like this, looks kind of messy. I'll try not to make a triangle. But I just randomly colored these edges. Oh, I missed one. We see, just by doing that, that I've got this red triangle at 137. I've got another red triangle at 147. Got a blue triangle. Okay, Ramsey theory and Goodman's result tells me that has to happen. Mathematical pareidolia would say 1, 3, and 7 have some real connection. There's some reason that those are all connected. I want to figure out a way to parse from a data set Goodman's result, which says a bunch of these have to happen. And I may have a graph that actually there is something real going on. And I need to figure out how to do that, because data mining wants to find these patterns. Okay, so this involves large data sets. We're searching for patterns. Typically, they're looking for correlations, but it's essentially the same thing. This, what I'm about to do, is due to Paliuk and Waddle from 2019. And so this is quite recent. I was surprised to find. When I was researching the book, I thought someone must have done this earlier, but no. So I will give the caveat that I made some corrections to their paper when I wrote the book. So there are some issues, but it's their idea. Okay.
Do they use Ramsey theory?
They used Ramsey theory. So everything Ramsey theory was fine. The statistics was not quite correct.
Do you tell them?
No.
You should.
Okay, so what I'm going to do is I'm going to consider a school board. So I just want to keep this small. Now, let's say what the example that they did was they looked at voting members of Congress. And so they were trying to show that certain members of Congress vote the same way. Well, Republicans vote the same way and Democrats vote the same way. So there's not a whole lot of surprise in what the results show. But on a school board, you don't necessarily know any political affiliation. That's not why they're voted in necessarily. So you want to know, is there a group here that kind of always votes the same way? And so that would be a pattern that is interesting, as opposed to, I know that there's going to be a bunch who vote the same way from time to time. We're looking for something over a series of votes. And so what I have here is I've got 7 members, and I've have them each voting 5 times just to keep the numbers small. So 1 is a yes vote, 0 is a no vote. And what we want to do is take the Hamming distance. So just how many places do they disagree in? And so if 2 have exactly the same sequence of votes, then the Hamming distance is 0. If all 5 are different, then the Hamming distance is 5. So I have 6 different possible weights that I can place on the edge. So I placed some of them here. So we can see that at the bottom of those that I've placed, those are the 2 closest to each other. None of them are the same. I made sure of that. So this is the closest. This might be the farthest away from each other in terms of voting. Okay, so this is in preparation for what's called the threshold graph. So we're looking at 2 colors, and we have on the edges, we have this weight. The threshold graph, which I'll label G of T, colors the edge between vertex I and vertex J red if that weight is less than or equal to T. So what I've done here is I've constructed G of 2. So everywhere you see a red edge means that the Hamming distance is at most 2. And then the blue means it's 3, 4, or 5. And so we get this graph. And as you vary T, obviously this graph will change. So it'll eventually be all one color. That is going to be what we consider our data. So our data is, so I let W be the maximum weight. So in my last example, that was 5. But in general, our data are the threshold graphs with T going from 0 up to W. So we have this data. What do we compare it against? Well, we don't want to compare it against a random graph because I know that the edges, if I look at G of W, everything is less than that. So the probability is very high that I'm going to have a red edge. So the probability needs to come into play. So what we're going to look at is R of P is the process of randomly coloring an edge red with probability P. And so necessarily it's blue with probability 1 minus P. So I've got this random graph, but it's based on P. I'm going to, and this is where I would disagree with them, they used each edge is equally likely. So they used P as 1 over W plus 1. I would argue that it's better to consider the distribution of Hamming distances, which is binomial. And so you should look more for binomial here. But they just used this, I guess, to convey their method. So with that, I'll define the random variables x of t as, and choose 3. And then this right here would be the probability that my edge weight is less than or equal to t. And so this would be all 3 are red. And then the other would be all 3 are blue. And so I'm looking at monochromatic triangles under this random process. And here's where Goodman comes in. I know that I have a minimum number of triangles that have to appear. So I subtract that minimum. Then what x of t is the expected number of monochromatic triangles in excess of Goodman's guarantee. And so if this random variable is large, then I might be able to say something's going on because I have a significantly more monochromatic triangles than Goodman's result says I will under the tenet of Ramsey theory. And so that is going to be the distribution we look at. So we want to test if our data, which is the threshold graph, the number of monochromatic triangles in that threshold graph, does that have a similar distribution with my random variable xt? So this is a chi-squared goodness of fit test. And so the test statistic is chi-squared with W degrees of freedom. And we can write down what that is. And so we can then apply the typical hypothesis test standards that we would use. So our hypothesis test would be that X and Y have similar distributions against, they are not distributed the same. And what that would allow us to do is say that we actually do have, if we can conclude that our alternative holds, we do have some meaningful connections going on in our graph. In terms of the school board, we would be able to conclude that yes, there is some kind of similarity of voting between certain members. It's not just happening because things are quote unquote big. You can also compare subgraphs against each other. So maybe you have a very large set. You want to know, does this particular group of, say, Republicans vote like this particular group of Democrats? So some kind of subset of each of those. You can compare those against each other to see how they vote. And that becomes an F test. And we have the framework to do it based on what we had before. So we're checking to see if they have kind of the same variance going on in this. Okay, so I guess I am, what, 2 minutes early? Thank you. So I'll take any questions you have.
And let's unmute and thank Aaron for a great talk. Any questions? We have time for questions. So I have a
Aaron,
question.
have you thought that maybe instead of trying to refute the findings of the Bible code, of writing your own Bible code to make a bunch of money? Because I mean, allegedly you could find whatever you want in there, right?
Exactly. So I could just, yeah, I could probably re-release the book I just wrote and show that there's secret messages in a math book. But I wouldn't want to spend my time writing another one.
What would happen if you apply it to, say, DNA sequences, right? So can
Yep.
you somehow conclude that life is inevitable?
So, yeah, I mean, you can do the same thing. DNA sequences just are 4 colors. And so you can conclude that there are, there's an arithmetic progression probably of length thousands with the same, I can't remember the letters. One of them's A. So that doesn't mean anything. It just happens. And so if you have a scientist trying to look for those kind of secret meanings, again, there's nothing going on.
But on the positive side, with this beautiful, first you were probably too modest. You probably significantly corrected the work of the people you mentioned. So
Yeah.
I think, and anyway, was it possible to test this method on real data?
So they did use, they used some real data. Reading through their paper was kind of muddled. But I have not myself independently used any real data to do this. So more of a framework where, yes, there's a way to do it. I'm not sure if it's the best way. It's more, to me, a cautionary tale that you need to consider things that are guaranteed to happen. And you need to look above that threshold.
Another quick question.
Yep.
Goodman is about triangles. Are there extensions to K4 and beyond?
No, it becomes very, very difficult very quickly. Yeah, it's surprising because the proof is, it's a simple observation, but once you get into anything bigger, everything falls apart.
Even with computers.
Yes.
Any other questions or comments? Well, let's thank Aaron for a great talk.
Thank you for having me.
And then next week is David Nashil. Hope to see you then. Bye-bye.
Bye.
All right, bye everyone. Thanks for coming out.
Thank you.